Boi Faltings. So while he's setting up, let me say a few words about him. Boi runs the Artificial Intelligence Lab. Kind of a good name. Has it always been called Artificial Intelligence Lab since the first day?
Yes.
Okay, so since 1987, okay. Artificial intelligence since 1987. He studied at ETH and then did a PhD at the University of Illinois, Urbana, and then joined EPFL and created this Artificial Intelligence Lab where, of course, he's been full professor for a long time. He's founded multiple companies. Multiple companies came out of his lab. Too many to list, but one that maybe a few people in here know, NextThink, which is one of those companies that keeps the VC investment stats look good for the Canton of Vaud. So without much further ado, please welcome Boi Faltings.
Okay, thank you, Marcel. So I'm in artificial intelligence, not primarily in machine learning, so I'm more a user of machine learning. And in fact, in AI, we see machine learning as a great way to build models for AI systems that are supposed to do smart things for us. And one of the difficulties that you find with this is that the AI systems typically have some influence on their environment. And so the training data that you collected when the AI system was not present often is actually not really representative of what you will find later. And so the knowledge that you learn is not really valid. And so what I'm going to talk about today is actually how you see that effect. And I'm going to concentrate on recommender systems. How many people here are interested in recommender systems? Yeah, quite a few. So you will find this talk interesting, I hope. And I'll talk a bit also about how to correct this effect. So recommender systems are very popular research topics. It's an annual conference just dedicated to the subject, which attracts over 500 participants, and is also quite widely used in practice. And in some sense, you could say it's a very typical application of machine learning AI, maybe one of the earliest ones that's been around. And what I want to focus on is that there's some gap between the academic research, in which we use a fixed data set, typically, of behavior that has been collected without a recommendation system being present, or at least with a different recommendation system than the one we're going to be using afterwards being present, and the actual application in which the recommendations, of course, influence the user behavior. So the area where we looked at this, we actually worked on recommendation in my lab for, well, almost 20 years now. My second company was in recommender systems, my fourth and fifth actually as well. So I've actually been quite active in this field. And one thing we tried to float, actually unsuccessfully so far, not commercialized, is news recommendations. And so news recommendation was once a very hot topic because the idea was that newspapers could actually make money online by selling ads to readers. Today, this model has not really worked, so you see newspapers disappearing. They'll probably continue. But the idea was always to keep readers on the site to increase revenue. So typically, readers come to you from Google or somewhere, and then they only see this one article. And in order to somehow sell ads, you have to try to keep them interested and make them stay on your site. And so you typically don't know anything about whoever is coming to your site, so you can only do a session-based recommendation where you personalize based on what you see during that session, and you have to somehow tune the algorithms to user behavior. So here's one screenshot from one of our systems that was running on Le Point, so you show these kind of additional articles that you might be interested in if you were interested in the ones that you've read before. So there's now a difference in the way you could evaluate this. So what we would really like to evaluate and what we'd like to train our algorithms for is to optimize the behavior online. That is the user behavior when they're exposed to these recommendations, and do they actually click on these things or not? And if I use one algorithm and another algorithm, how much of a click-through rate do I get? Now the problem with that is that I'd have to test each of these algorithms separately in an online setting. And that's very costly because you have only so many clicks. Even on a site like Le Point, which is one of the biggest sites in France, you get only a few million clicks every day. And so that's not really enough to do very systematic tests. And the other thing you can do is to test on offline behavior. That is, you collect data of what people have read and in what sequence they read these things. And then you can try to use that to optimize your algorithm, try to predict whether you could sort of predict correctly what people looked at. And of course, this offline behavior, it's a bit like the person who's looking for his keys where the light is and not where he lost them, because clearly you want to help people find other things than what they already found anyway. But it's, for academics at least, often the only way that they can do research, because it's just out of the question to really test things in real life. So unless you're working for Google or Yahoo or somebody that has a very large web property, it's almost impossible to develop these algorithms. So almost all academic work, including, for example, the Netflix prize, has used this testing on offline measure. And so the question is, of course, is this offline actually a good proxy for online? Clearly, you're not going to get the actually correct click-through rates, but can we at least sort of qualitatively use this to compare algorithms to tell which one would be better than another? And so we can define similar accuracy metrics. So the accuracy metric cannot be exactly the same, because in one case we would be measuring click-through rate, and in another case we can only measure what we call the success at k. And we say that we have a success at k if the next viewed article is in a set of recommendations of size k that our algorithms would make. So typically you can tune the algorithm. You could make very few recommendations, only the most likely ones, or you can make many of them. And of course, your site can only display a few of them. You don't have so much space, so that typically determines some k. So offline, that's typically the measure you can have. Can you predict what people looked at? Because that would be the articles that they like in this case. You could say something similar about other product recommendations and so on. And online, of course, we could really observe the click-through rate. That is, does the user click on our recommendation or not? So was it successful or not? So we did this with a number of different recommender algorithms. Actually, the interesting one is the last one, which is a variable order Markov model, which is the one that we actually built based on context trees. And that one really learns from user behavior to recommend preferred items. But we benchmark against two other ones. One of them is to recommend the most popular items, and one of them is to recommend just random items. Okay? So here's the offline accuracy we found. So that's fairly typical of sort of academic research. You find that most popular works best. That's actually very often the case. Many academic papers do not do that test, but most popular is a pretty good algorithm with this kind of evaluation metric. Our algorithm performed almost as well. So that's not bad. And random is all the way at the bottom. Like you can see that dotted line, or you can hardly see it. So it has almost no success at all. So we would conclude here that most popular is the best algorithm. Actually, often people use matrix factorization. That's very close to the most popular one because it has a very heavy bias to very popular items. Without being a very strong personalizer. So context tree didn't come out too poorly. So now, when we put this online, so we had the chance with news organizations to put this online, we actually observed something a little bit different, which is that, first of all, random was the best. So this is, since the algorithms require some tuning over time, so you see the tuning periods here in days of running on that website. So the random one, well, was a little bit random behavior. So we don't really know why it was so high on the first day, or on the very first moments of the first day. But it kind of stabilized to a click-through rate of something like 6%, which is actually pretty high for news sites. The context tree was about equally good or slightly better, so we're sort of happy about that. And the most popular one now falls a fair deal lower. Of course, you can understand this because if we are predicting always an article that a person would have read anyway, very likely he's not going to click on our recommendation. So the training that we did is not all that accurate, but what's more maybe disturbing here is that actually the order of these algorithms is completely reversed. So at least in the initial period, random is the best one, and then the context tree comes up, well, at least in some part of this, and the most popular one ends up being at the bottom. So what does that say about academic research where we are limited to this kind of offline evaluation? Well, it's really not that great. Now, one quick word, if I do have a moment, about these random recommendations. So they look like they're really good here. Actually, that's a little bit of an artifact. So the first thing is that the random recommendations, of course, people may be curious, so they may click on those. It's a particular feature of news. We don't really have a feedback whether they actually like those articles. And the other thing is that actually very often we have no data at all. That is, most of the visits, so the random one is actually fairly strong on short visits, because on very short visits, we have very little data about the person who we're making the recommendation for. And so the trained model is quite inaccurate. And actually, it turns out the random model for visits of length 2, for example, so it just one click, so the page where it landed, and then one recommendation which we can evaluate, so that's the shortest visits. Random is actually better than the learned one, but for longer visits, the learned algorithm actually takes over. And unfortunately, most of the visits are very short. So that's the fact of life for news sites. And so when you take the whole thing together, random ends up being very good, but actually it's not such a great recommendation technique. But still, random can be important because one of the ways that we could do better is to say, okay, the reason why we get this wrong evaluation, why we draw the wrong conclusions based on this offline evaluation methodology is that we are actually giving people recommendations of things that they've already seen, and we are basically not taking into account the influence that we're having. And so one thing we could do is to say, well, let's give random recommendations, so it's like a system that has no smarts, but in part of the traces, we're going to find actually the same behavior. So we could sort of simulate all the possible recommender behaviors if we have a trace that was made with random recommendations. This is a proposal that was made by a bunch of guys from Yahoo in 2011. So you collect logs with random recommendations, and then in those logs, you are actually, for whatever sequence you have, you're likely to find that sequence of articles that people read in that log somewhere, maybe several times. And so you can see what the frequency is of the next items. And so what would have been actually a good recommendation that you could have made. And here, now, these next items are not items that people found by themselves, but items that they found through a recommendation that was made by the system. So you have a very realistic scenario. And this actually worked pretty well. So for the Yahoo guys with this, they managed to predict the true CTR pretty well and actually get an evaluation that was quite meaningful. The only problem is that in order to get a good chance of finding these sequences, either you really have to have billions of clicks, or you have to have very few items. So Yahoo's homepage, where they did this, had only 20 different items to choose from. And so if you take a sequence of length 3, for example, then you only have a couple of thousand possible sequences. So with millions of users, you pretty soon have quite a good sample for each possible sequences. So it doesn't really work for real news sites where you have thousands of items and this random generation will only show a few of them. But it is a technique that would be kind of clean and that will work. So what shall we do when we have something like news or, well, product recommendation where we generally don't just have 20 items, but we have thousands of items at least, and sometimes millions of items? So I would propose a different method. And that method is kind of an engineering trick, but it works actually fairly well. And the idea is to do an offline evaluation, but not just with this accuracy criteria. So I will argue towards the end, and I will show you that the accuracy criterion actually is not necessarily the right one to predict the online behavior. It's correct for predicting the offline behavior, but it is a poor predictor of online behavior. So instead of that, we'll use a number of different evaluation metrics that I'm going to show you in just a moment. And then we're going to do some online testing with the purpose of finding out what is the predictive power of each of these evaluation metrics for the actual online performance, for the actual click-through rate. So for that, we need some online testing, but we don't have to test all the different algorithms. We just have to test these evaluation metrics. And so that's much more doable. That's really not that hard compared to tuning our algorithms in an online setting. And then finally, we can put the two together and use this mapping, this regression model, to predict the online behavior of different algorithms and then the optimal tuning for them, right? And so what evaluation metrics could we use? Well, the literature on recommender systems is rich with lots of proposals. So accuracy is clearly one of them. That's the one that everybody naturally optimizes. So is the recommended item actually chosen? But then there are others, like diversity, for example. So how dissimilar are the different recommendations? There's coverage. So do we actually have scenarios where all of the items are recommended sometimes? Serendipity, is it somewhat unexpected? Novelty, is it a long tail item? So there are lots of these metrics that have been proposed over the years without ever having a quantitative evaluation of what they actually say, right? So this is the shortcoming. People have been saying, yeah, we know that diversity is important or serendipity or whatever, but I have nothing to prove it. Well, we do have something to prove it now. So what we actually did is to do this modeling for how predictive these different features will be of online performance in news recommendation. And we used least angle regression for feature selections to figure out which of these are actually the most predictive ones. And for those of you who are not familiar with that, so you have a regularizer that minimizes the number of features, and you gradually decrease the weight of that regularizer so that you allow more and more features, and you see when do they enter the model. The more important ones will enter it earlier and the other ones later. And here what we find is quite interesting. So this was on data actually earlier with Swissinfo. It's a slightly smaller site. It's run by the Swiss government for information about Switzerland, where we graciously were able to run our system for multiple years. So it was quite nice. So here we see the first one is so we grouped all these metrics into groups. So we had these 5 different groups, and we had different examples of these metrics. So the first one that was going to enter in this least angle regression was personalization. I actually don't remember what exactly the definition is, but it is a kind of diversity measure. So it measures how different the recommendations are from one another. The second one to enter was serendipity. And then in the third one, we do find accuracy. So accuracy is important, but it's not the most important feature. And then we get coverage and novelty. Those were not actually quite that high. It's probably maybe due to this particular case. So if you have access to a site with a lot of traffic, would be great if you do these kind of experiments. You could maybe come up with different results. We should form some kind of average. I mean, I think it would be nice if those who do have access to the data, which is pretty rare, unfortunately, among researchers, we could actually try to better understand quantitatively how important these features are. Anyway, so what we can do then is we can see how good these regression models actually are. And so we see that they're actually quite accurate. So the RMSE, the root mean square error, is only about 0.5% of actual CTR. And so if we build this regression model with these features, and we are at least 2 times better than just using accuracy. So you can see some predictions here for the. So this is the online click-through rate, but predicted with offline data. And you can see that for 2 different strategies here for the context tree, we have always, that one is in blue. We have the dashed line is a predicted one. The solid line is the real one. And we are kind of pretty close to that. And for the most popular one, similarly, we also can get pretty close to an accurate prediction. Right? So we think that that's a pretty nice technique. So this is both, by the way, with the same regression model. So we can hopefully get the same kind of accuracy if we take other algorithms and we can compare online and offline. We can maybe, again, predict the true online behavior and then use that to optimize and tune those algorithms much more realistically. So the methodology could really be that maybe this doesn't only apply to recommender systems, is to develop somewhat broader performance measures rather than just a loss function of accuracy and so on, which maybe doesn't apply to the data because of this discrepancy between training time and runtime of your system. And then train a model that performs this mapping for you, and that would allow you then to actually optimize this online performance, but only use offline data. So in conclusion, I presented at least one example of, I think, something which is quite frequently a challenge when you use machine learning in AI, is that the training data is often not representative of the application, of what you find when you actually apply the system. And so the cleanest thing is to collect the data with random actions. I was proposing an alternative, which is the last one, which is to learn a model that would map the offline performance to online performance. What actually can happen also is that you do some kind of incremental deployment. So you start with a model that's not that accurate. You see what happens. You do a kind of reinforcement learning. You adapt the model to the new data that you observe. That's something that you could also use. And that's, of course, a little bit more tricky maybe to evaluate because it has to converge. And so it could also be an alternative technique if you actually have the online environment. OK, I'm done with that. And I thank you very much for your attention.
Many thanks, Boi. Any questions? Did anyone lose their phones?
It's very hard to see anything here.
No phones lost? OK, good. Any questions? No? It's a machine learning overload.
Yeah, probably.
OK. Well, thanks again very much.
Good.
Thank you, Boi.
Thank you very much.
There's a question. There is a question.
Oh, there is a question. Oh.
I volunteer for a question. Are the algorithms for everybody, for the crowd, for the whole people, or they are people specific? So every person on the internet have a special algorithms of what he likes, what he or she doesn't like on the
No,
internet?
whenever somebody comes in, you get a random assignment. So whenever the person lands on the site, then you randomly assign them to one of the algorithms. So you get a roughly equal population for each other.
We have all different tastes. Some people like sports, and other people like politics.
Yeah, so you get this, hopefully you get the same mixture across the, because we have quite a lot of users. So